Welcome to Technical Mentor channel. Today we discuss the topic of filter design, which removes DC drift and 50 Hz noise at the same time. We design ideal filter response with zero transmission for DC drift and 50 Hz, but leaves other frequency intact. Here we have to do inverse Fourier transform numerically defining your ideal frequencies for the vector, and they're transforming it into the time domain to obtain the impulse response. Also, we do here my filter function to develop input signal, and we will use here band stop filter to do this. So, to solve this question, first of all, we have to see theoretical work which I have already developed. In step work, we used single filter. In the previous work, we saw that by using single filter to remove 50 Hz noise and DC drift, in this step we have to use high pass filter to DC drift and noise. In high pass filter, we use 1378 taps to prevent any signal, and also in step 3 we could include Hannock window is the optimum function for filtering with a single filter. Formula which we used in high pass filter is this: for n is equal to 0, n is equal to non is not equal to 0. Here we create cutoff frequency and convert it to radian per second using this formula. And then use high pass filter formula set 1 when n is equal to not is equal to 0. So high pass filter is this, and when value is equal to 0, then we use this formula. Now compare the two figures below. Tabs number in this step should be adjusted and then signal start at same magnitude. Here tab size is 1378. We know that high pass filter only removes DC drift, but 50 Hz noise is still present. Therefore, we use band stop filter to remove 50 Hz noise. The band stop filter equation is this: for n is equal to 0, and this for n is not is equal to 0. Now we implement these techniques in the MATLAB. We delete previous graphs. Okay. First of all, we use high pass filter to remove DC drift, which we have already discussed in the previous window. We do some steps: step size, cutoff frequency, and FHP, tap axis, and convert it to radian per second. And we use high pass frequency formula for n is equal to 0 or n is equal to not is equal to 0. Now we create a figure to check the high pass filter. So implement this and we got this result. Now we use our function myFIR to remove DC drift. Okay, and plot the result in time domain. Okay, you can say data in the time domain. Now we plot the data in frequency response. So we use Fourier transform on the data and then plot the data. Okay, you can see the result in frequency response. Okay, now we check the data after filtering the data and in frequency response, frequency range. Okay, This is after filtering. Now we use band stop filter to remove noise. DC drift we already removed, but noise is also present. So we use band stop filter technique. Here we initialize some variable f1, f2, fs, fbs, w1 using formula, w2 using this formula, and change this. We can change this to 1300 8, but here we keep 1300, and nsbs using formula from this to this. FBS 0 sampling size this to this. Tab axis should be from 0 to cutoff frequency. Now we use band filter formulas to get the result. So we implement the technique. So saw what is the result using band stop filter. Okay. So this is our result using band stop filter. You can see the result. Now we apply our filter which we have developed in the previous video. We initialize a filter according to our data. Okay, and we use our filter function, and then we check the result in frequency response. So we use Fourier transform to check the result in time domain. You can check the result here. We have removed some noise but still present. So we check the result in frequency response, which is this frequency domain, and we check the result after frequency, after filtering the data. So we implement this. You can see that we have removed some noise here. You can see the result. Okay, thank you so much.